Okay, today's lesson is going to be rather quick. I'm just going to go through one example. We're continuing on with the idea from section 11D that if we have a system of equations, we can translate it into an augmented matrix and then use elementary row operations to reduce it down into row echelon form and then use back substitution to solve our system. So there's three possibilities when you're trying to solve a system. You could get one solution, which means a value for x, y, and z that satisfies all three equations, and that's the only values for x, y, and z that satisfy all three equations. You could have no solutions, which visually is equivalent to saying that you have three planes that are all parallel. And you could have infinite solutions, which could either mean that the three planes are all the same, or that they all intersect in a line, and therefore the line has an infinite number of points. So we would have infinite solutions in either case. All right, so let's consider this system here. And let's use row operations to solve this. So the first step is let's write it in our augmented matrix. So we have 1, 2, -2, 5. And then 1, -1, 3, -1. And finally 1, -7, k, and -k, or the opposite of k. There's our augmented matrix. Okay, so now if you remember, the idea is to use the first row and looking at that number in the first column and eliminate the second and third row's first entry. So we want those to be 0, and we're going to use the first row to do that. All right. So let's use our notation. If I multiply row 1 times -1 and add that to row 2, replacing row 2, that'll put a 0 in the first entry in row 2. So I'm not changing row 1. So 1, 2, -2, 5. And now, when I multiply the first row by -1 and add it to the second row, I'm going to get 0. -2 minus 1 is -3. +2 plus 3 is 5. -5 minus 1 is -6. All right, now let's multiply the first row by -1 again and add that to the third row, replacing the third row. And that's going to give me a 0 in this spot. So that accomplishes my first goal. And then I'm going to have -2 minus 7 is -9. And then +2 plus k. And then finally -5 minus k. Okay. So there we have that. All right, so now the next goal is to try and get a 0 in this spot. And so I don't want to use the first row to do that because any multiple of the first row added to the third row will change that 0 to a number. And I want that to be a 0 in the first spot. So I'm not going to use the first row, but what I'm going to do is use the second row because anything times 0 added to 0 is still 0. But then I want to multiply this by something. When I add it to this, I'll get 0. And obviously that's a -3. So my notation is going to be -3 times row 2 added to row 3, and I'm replacing row 3. So the first row stays the same, 1, 2, -2, 5. The second row stays the same, 0, -3, 5, -6. But now my last row, I'm going to do -3 times 0 plus 0. And then I'm going to get -3 times -3 is 9 minus 9 is 0. And then -3 times 5 is going to be -15 plus 2 plus k is going to be k minus 13. And then I'm going to do -3 times -6, so 18. plus -5 minus k, so it's going to be 13 minus k. All right. So now we're at the point where it's an upper triangular form and we could use back substitution to solve. So before I do that, let's look at the next question because it kind of ties in with what we've done so far. For what value or values of k does the system have infinite solutions? So by now we've learned that if this last row is all zeros, which would mean if k minus 13 is equal to 13 minus k, then our last row, and if I translate that back to a system, is going to read 0x plus 0y plus 0z equals 0. So basically 0 equals 0. So now what I really have is a system of two equations with three variables, and that's going to give me infinite solutions. So if k minus 13 is equal to 13 minus k, and I solve that, I'll get 2k is 26, and I'll get k is 13. So when k is 13, I'm going to have infinite solutions. And now it says find the solutions in this case. So let me copy this. First, let's move that out of the way. All right, let me group all this. And then let's clone it. Science before your eyes. Okay, so if k is equal to 13, then our system is going to become x plus 2y minus 2z is equal to 5, and negative 3y plus 5z equals negative 6. So if you remember how we dealt with this, what we'll do is we'll say let, and I could pick any variable actually, but the standard convention most of the time you'll see in textbooks is they'll use the last variable, z in this case. So let's let z equal t, that's our parameter. And so then now my second equation becomes negative 3y plus 5t equals negative 6. So negative 3y is equal to negative 5t minus 6. And therefore y is equal to 5/3 t plus 2. So I've got z is equal to t, y is equal to 5/3 t plus 2. And now going back into the first equation, I can solve that. So I'm going to have x plus 2 times y. Well, y is 5/3 t plus 2. Minus 2 times z, well, z is just t, equals 5. And now I can solve this for x. So I'm going to get x plus 10/3 t plus 4. And I'll move that to the other side, so I'm going to have equals 1. And then I'll combine the t's. And 10/3 minus 2, so that's minus 6/3, so I have 4/3 t. When I move it to the other side, I'll have negative 4/3 t plus 1. And so now I can write the solutions to this system as an ordered triple. I guess I'll do that in red over here. Find the solutions in this case, so that would be negative 4/3 t plus 1, comma, 5/3 t plus 2, comma, t. And if you let, let's say x equal to t and try to work that way, or let y equal to t, then you'd have a different looking answer, but it still would represent all the solutions. Okay, so we got one more question. And it says, show that there is a unique solution for all other values of k, and then find the solution in terms of k. So let me go back to this, copy this again. I'll use that. All right, so let me write this system out for what we have right now. So what we have is we have x plus 2y minus 2z is equal to 5. We did that already. We've got negative 3y plus 5z equals negative 6. And then the last one, we have k minus 13 times z equals 13 minus k. So this is an upper triangular form, so we can use back substitution. So let's start with the last equation. I have k minus 13 times z equals 13 minus k. And if I divide both sides by k minus 13, I'm going to get z equals 13 minus k over k minus 13. Obviously that's undefined when k is 13, but we've already dealt with that case already. So if I factor the top, I could factor a negative 1 out of the top and it would become negative 1 times the quantity k minus 13, and those cancel. So this actually simplifies down to z is equal to negative 1 as long as k does not equal 13. So z is negative 1. So now we'll go and work on the second equation to solve for y. Negative 3y. If I plug in negative 1 for z, I'll get minus 5 equals negative 6. So negative 3y equals negative 1. So y is equal to positive 1/3. Okay? And then I will use those values for z and y into the first equation to solve for x. So x plus 2 times y, so that'll be 2/3, minus 2 times z, and z is negative 1, so plus 2 equals 5. And so when I solve that, I get 2/3, 8/3, 15/3, I get a positive 7/3 for x. And so therefore, find the solution in terms of x. I'm sorry, in terms of k. Well, all I have to do is specify that k does not equal 13. So my solutions are, let's write this in black, I guess. So let's go 7/3, comma, 1/3, comma, negative 1, and then specify as long as k does not equal 13 for this system. And if it does equal 13, we've already answered that. So hopefully that makes sense to you. And for the homework assignment, only have a couple of problems in section 11D starting on page 264, and hopefully that'll go well.